So basically, yeah. So once you've kind of like applied enough of the convolutional layers to this thing, then the next thing would be you kind of aggregate all of that into a single vector, and you apply that to a dense network. So dense network is basically a fully connected feed-forward network. So it's just simply a neural network where all the nodes are connected to every other node. And that's a standard neural network. So then once you do that, then you pass that on to the neural network. And the difference, though, is that the backpropagation value for a convolutional neural network will also update the kernels as well. So it's not just the weights, but also the kernels. So in effect, what's happening is part of the training process, you're training it by also figuring out what are the right, how do you extract features more efficiently. So the feature extraction process is also updated as well. So it's learning how to extract features. So it's really cool. So the way that, and so what I was saying though is that based on the feature selections that you have, if there's a lot of variability in the data, then obviously, as we talked about, it's going to have trouble like keying off of something. If there's very little variability, then you don't need that much data. So that is a determinant of how much data, one of the determinants of how much data you need for training. If the data elements are very similar, then chances are it'll pick up patterns really quickly. Very complex, it requires a ton of data then to be able to do this, to encompass a lot of variability. In some cases, it's almost impossible, like in terms of how you actually do that.
So let me start with recurrent neural networks. So they were actually pretty old. They've been developed. They started. So recurrent neural networks were developed in the early '80s. So they eventually, 1997, a type of neural network called long short-term memory, or LSTM, was developed, and this is a more robust way to do recurrent neural networks. And essentially what they're used to do is they're designed for analyzing sequences of data. So you'll see a very frequent reference to them. In fact, when we talk about the sentiment model, you will see that we use an LSTM network there. And the reason why you have a sequence is simply because of the fact that you have a sentence, and a sentence is a sequence, and where you have the previous things depend on the next things. So that's kind of why LSTMs work. So LSTMs basically identify relationships between kind of previous and next data. They're used a lot in NLP projects, so you'll see them appearing all over the place there. So yeah, so we're going to kind of cover that. And they're just basically a type of RNN. So as the name suggests, an RNN is simply like a recurrent neural network where you have a bunch of inputs and outputs that are related in some way, and the neural network effectively tries to form a connection between them. And the way it does that is it takes the state of the previous iteration and feeds that into the next iteration as one of the inputs. So it's not just simply the input, it's not just simply an input. When you do the training off a recurrent neural network, is not just simply just taking into consideration the input, which is normally what you do with like with backpropagation in a standard neural network. It actually takes the previous example as part of that input into the next iteration. So that whole process is kind of like a recurrent neural network, and that's how it relates the previous terms to the next one. So the overall process is very simple. The idea is simple, but of course everything is not so simple. But basically, the way you think about it is that you have an input going into your model that generates a state which goes back into the model with the next input going in, and so on and so on. So it's basically, it's an iteration. So you can kind of fold it out like this. So you have so if you have a sequence of data, in this case, let's say an x1, so y1, x2, y2, x3, y3. And what you're doing is you're transitioning from x2 to x3, which implies that there's a y1 to y2 to y3 translation. Then that overall process means that this is something where, because the previous state depends on the next state, that would be an example where you use an RNN. The way you kind of do this is kind of like almost like a standard training set. So you basically put it into your system, and it goes, it's just like any other neural network. So you start off with that. But then what you do is then when you go to the next iteration, so normally with a normal neural network, the next iteration is just dependent on the next input. But now instead of that, you actually have a state that comes from there, and that also combines to generate the output. So as part of the training set. So what it would look like is that your initial input would be x1 and y1, and then so the state, this is the state, and that's kind of like nothing at the beginning. So output. So then the next one would be x2, and that's kind of dependent on that. So the state has now changed. So you kind of like go into s1, and that goes into y2. So basically, you have sort of kind of x2 plus s1 goes to y2, and that's the next in your training set, and then goes to s3. So you've got like x3 plus s3 going to y3. Now, the thing is, this part is automatic, so you just, as far as your AI is, as far as training it is concerned, it's a simple input and output. So you have your input and output as part of your training set. But this part there happens implicitly when you train a recurrent neural network. So in terms of how that works, more mathematically, so you have basically. So you have basically the x input at time t, and so this is going in there. So you have basically three matrices, which is u, v, and w, and you have a hidden state of the system, s, which basically changes over time. So then what happens is that when you update the system, it'll update kind of, so you have u and v changing, and then it'll kind of go, you'll have a weight matrix which basically goes into the next one. So in terms of how that would work is when you first do that first iteration, the output is a weight matrix as well. And then it'll combine with the next weight matrix and kind of produce new output and so on. So the output at time t, this is basically a standard, so it's a Vx, so it's basically a simple output at that. And then the state itself, you'll have some sort of like nonlinear function, which is a sum of the input, so xt. So this is exactly what I was talking about there. So you'll notice that you have like an input matrix there, so u going into that, and then you also have the st, which is so u going into that, plus you have an st, which is the weight matrix times the previous state. So the final thing is basically the sum of the input of the previous state and a matrix operator onto the new state, and then you calculate get an activation function, for example, ReLU, and then you kind of move it. That's how you calculate the next state. So so one of the things is you use RNN. RNNs use backpropagation through time, which is a little bit more complicated. So it's not a straight, I'm not going to go through that, but it's not a straight backpropagation problem. But the concept is the same. You're essentially calculating a derivative during this process. And so you're still going to you still have to calculate the gradient going to 0. The problem is one of the challenges is that the way this would work is that sometimes you have two situations that could develop where the gradient just directly goes to 0 very quickly, which is not good, which is a problem in this case, or you can have the gradient exploding, which is also a problem because it means you'll never get convergence. And so this is a challenge that you sometimes will run into with RNNs. The other thing that'll happen is because when you actually sort of do the math, and so basically this is an iteration. So if I were to plug in xt, so if I were to plug in st minus 1 and actually to go through this, what you'll end up seeing is that as you progress, you end up with an exponential decay of the previous state. So it forgets the previous values very, very quickly. So which means that RNNs on their own only remember the closest states. They don't really remember really distant states. So if you have a case where you have a very long sequence that you want the neural network to learn, RNNs are not, like on their own, are not the right way to go, or the vanilla RNN is not the right way to go. In which case then you need to use LSTMs, which is our next thing. So an LSTM is very similar. You have, again, it's like you have you have the kind of like the t minus 1, and then you have a state going across, and you also have the output going across into the next one. And so here it's a little bit more complicated because what you have is you have an input and output and forget gate. So the input gate is, as the name suggests, it's related to the input of the data. The output gate is related to the output of the data. And the forget gate is what's responsible for sort of discounting some of the previous values so that you can actually control the rate at which it forgets the previous value. So in the vanilla RNN case, it exponentially forgets the old data. With LSTMs, you can control the rate at which it does forget. So the way you think about it is you have, so in this case, you'll have W. So the process is, again, relatively straightforward. So imagine you've got three types of gates. You've got forget, you've got input, and you have an intermediate state, which is C. And so basically, if you calculate what these things are, so you have y of t minus 1 and x of t, so going in there. So this is taking this input, and you calculate f of t, or ft there. So that's one of the values, which is the forget side. So wf is kind of like it's a weight matrix that corresponds to forgetting. Then you have your input, which is again, you have a weight matrix associated with the input. And that, again, takes yt minus 1 and ct. And then you have another weight matrix corresponding to this value, which is kind of a state value. And so then what you do is you calculate, again, it's a weight function taking in the previous yt minus 1 and xt, and that calculates ct prime, which is this thing there. So essentially what you have is you've got x, ft, it, ct. So then the next thing you want to do is calculate the output. And so that's something that you want to do, and you again have like an output thing, which is a weight matrix taking in the input and so on, and you get an output value. So these are the kind of the core values that need to be calculated. And so as you can see, you need 4 different matrices for that. So then the next thing that you do is to calculate the CT. You take the CT minus 1 plus the value, which is kind of like the state transformation here, and you so it basically is responsible for the input, so you multiply the two together, and then you calculate the change of state there. And then the final thing is the y of t, is you take the state vector times the output value, and you get the new state, the new value of the output, which is kind of this thing, which is what you care about. So the output times the state vector, the tan of this hyperbolic tan of the state vector times is equal to the true output of that network. So what that does is that it gates several things. So it looks really complicated, but really what's going on is you have a function. We have a matrix that's responsible for forgetting the previous state, something which is and then you've got an input weight matrix, which is forming sort of the traditional matrix for a neural network. Then you have a sort of a state transition matrix there, which is kind of, again, taking a weight matrix for state transition. That gives you the sort of the next state transition, which is the CT. Then you have an output weight matrix, which calculates this OT. Combine all of that, and that gives you the next YT, which is the output of that particular transition. And then you kind of keep repeating that. So this solves several problems. One is it solves the vanishing gradient problem. The second thing it solves is it also solves the exploding gradient problem as well. So that's actually a really key. That if you look at, and if you actually calculate all of that, I mean, for example, what the sigmoid does is ultimately converts it into a value between 0 and 1. And what all of these things do is that, and this is like a -1 to 1 and so on, what they all do is they force the values to stay within a certain range. So you never get an exploding value, you don't really get getting to 0 quickly. This is, it's a more complex mathematical idea, but it is the same idea in principle around recurrent neural networks. And so when you calculate the backpropagation for that, you're simply doing a backpropagation based on, it's a time-based backpropagation as well.